Hey there. How's it going? Thanks for joining me today. Whether you're relaxing at home on your commute or winding down for the evening, I'm really glad you're here. 4 billion years ago, something extraordinary happened in a place we'll never see. In a solar system orbiting a star whose light hasn't even reached us yet, a cosmic catastrophe unfolded. Picture this. A young star surrounded by the same swirling disk of gas and dust that forms around every newborn sun. This disk is the raw material of worlds, the building blocks of planets, moons, and everything else that might orbit a star. But in this particular system, something went terribly wrong. Before we continue this journey, tell us where you're tuning in from. And if this story resonates with you, make sure you're subscribed, because tomorrow I've saved something extraordinary for you. The details are lost to time and distance, but the evidence suggests gravitational chaos on an unimaginable scale. Perhaps a massive gas giant formed too close to the star and began spiraling inward, its gravity disrupting everything in its path. Maybe two forming planets collided, sending debris flying in all directions. Whatever the cause, the result was the same. Chunks of ice and rock, the failed beginnings of worlds, were flung outward with such violence that they escaped their star's gravity entirely. They became wanderers, cast into the void between stars with no home to return to. One of these fragments was destined to become something we would eventually name 3I/Atlas, an interstellar comet that would, billions of years later, enter our solar system and raise one of the most terrifying questions humanity has ever contemplated. For 4 billion years, this object drifted through interstellar space. Let that sink in for a moment. 4 billion years! Earth itself is only 4.5 billion years old. While our planet was forming from its own disk of debris, while the first oceans condensed from steam, while the first simple cells emerged and began the long journey toward complex life, this comet was traveling through the darkness between stars. The journey it made defies comprehension. No sunlight warmed its frozen surface. Out there, between the stars, there's nothing but darkness and cold that approaches absolute zero. No planetary companions orbited nearby. The only forces acting on it were the infinitesimal gravitational tugs of distant galaxies, slowly altering its trajectory over eons. It passed through regions of space that human eyes will never see, drifting past stars whose light is still traveling toward Earth, carrying with it the chemical signature of its birth system, elements forged in a different stellar furnace. Organic compounds assembled under conditions utterly alien to anything in our solar system. Then, in the spring of 2024, something changed. Astronomers at the Atlas Survey Facility in Hawaii were doing what they do every clear night, scanning the sky, looking for anything that moves. The telescope captures images of the same patches of sky repeatedly, and software compares them, looking for objects that have shifted position against the background of distant stars. It's meticulous work, searching for faint smudges that might represent asteroids or comets passing through our cosmic neighborhood. On this particular night, they found something unusual. A faint point of light, barely visible, moving against the stellar background. But it was moving wrong. The trajectory didn't match anything in the solar system's catalogue. The numbers told an impossible story. This object was moving too fast, at the wrong angle, with far too much energy to be gravitationally bound to our sun. Within days, telescopes around the world turned to track this mysterious visitor. Here's what's really happening when astronomers calculate an object's orbit. They're measuring its position very precisely at multiple times, then using orbital mechanics, the same mathematics that put humans on the moon, to determine where it came from and where it's going. For objects in our solar system, those calculations produce elliptical orbits around the sun. But for 3I/Atlas, the mathematics produced something entirely different, a hyperbolic trajectory. In simple terms, this object was just passing through our solar system. It wasn't orbiting our sun. It came from somewhere else, This made it only the second confirmed interstellar object ever detected by humanity. The first was Oumuamua in 2017, a mysterious cigar-shaped object that zipped through our solar system so quickly that by the time we realized what it was already on its way back out. Oumuamua raised more questions than it answered, and we never got close enough to study it properly. But 3I/Atlas was different in crucial ways. Spectroscopic analysis revealed its nature. When sunlight reflects off an object, different materials absorb and reflect different wavelengths of light. By analyzing this reflected light with spectrographs, we can determine what something is made of, even from millions of kilometers away. The data showed that 3I/Atlas was a comet, a mixture of water ice, frozen gases, rock, and organic compounds. As it approached the inner solar system and the sun's heat began warming its surface, the ice sublimated, transitioning directly from solid to gas, and formed a tail. This is the classic behavior of a comet, and it gave us our first real look at material. Formed around another star, the measurements told us it was approximately 400 meters across, about the length of 4 football fields, with a mass around 100 million tons. These numbers might not sound particularly impressive. In cosmic terms, this is a small object, barely a speck. But here's the thing about cosmic collisions. Size matters, but velocity matters even more. And 3I/Atlas was moving at roughly 30 kilometers per second relative to Earth. That's 70 times faster than a bullet, nearly 4 times faster than the space shuttle re-entered Earth's atmosphere. For a brief moment in its 4-billion-year journey, 2 star systems were connected. The ancient light from 3I/Atlas's birth star, frozen in the chemistry of its ice and rock, was meeting the light of our sun, the comet's tail, gas and dust. Streaming away from it was the first and only sample we've ever had of material formed in another stellar system that we could potentially study up close. But in the observatories and research centers where this data was being analyzed, someone asked the question that changes everything. It's the kind of question that scientists are trained to ask, the what if, that transforms an interesting astronomical observation into something far more urgent. What if it didn't just pass by? What if an object like this, moving at interstellar velocity, massive and dense, forged in another solar system, collided with Earth? The scenario we're about to explore is hypothetical. 3I/Atlas followed its trajectory safely through our solar system and is now heading back into interstellar space, never to return. But the physics of what would happen if it struck Earth is not hypothetical at all. We know what happens when cosmic bodies collide because the evidence is written in crater fields on every rocky world in the solar system. We've seen it happen in real time. In 1994, humanity watched something unprecedented. Comet Shoemaker-Levy 9 broke apart under Jupiter's gravitational stress and then collided with the giant planet over the course of several days. Each fragment that struck Jupiter released energy equivalent to thousands of nuclear weapons. The impacts created temporary holes in Jupiter's atmosphere larger than Earth, dark scars that remained visible for months. Telescopes around the world and the Hubble Space Telescope captured the entire event. For the first time, we witnessed the destructive power of cosmic collisions on a planetary scale. We've also studied the aftermath of ancient impacts on Earth itself. The Chicxulub crater, buried under Mexico's Yucatan Peninsula and the Gulf of Mexico, tells the story of what happened 65 million years ago. An asteroid 10 to 15 kilometers wide struck with energy exceeding 100 million megatons, 5 billion times more powerful than the atomic bomb dropped on Hiroshima. The impact ended the Cretaceous period and the age of dinosaurs. 3/4 of all species on Earth went extinct. The geological boundary marking this event, called the KT boundary, appears in rock formations worldwide. A thin layer of iridium-rich clay, sandwiched between rocks containing dinosaur fossils below and none above. Then there's Tunguska, On June 30th, 1908, over remote Siberian forest, something exploded in the atmosphere with the force of 10 to 15 megatons. An object, probably a small asteroid or comet fragment about 40 meters across, entered the atmosphere and disintegrated before reaching the ground. But the airburst was powerful enough to flatten 80 million trees across 2,150 square kilometers. No crater formed because the object never made it to the surface, but seismic stations around the world recorded the shockwave. If Tunguska had occurred over Moscow or London instead of uninhabited forest, hundreds of thousands would have died. Here's what makes these comparisons so crucial. 3I/Atlas is larger than the Tunguska object. It's smaller than the Chicxulub impactor, but it's moving faster than either. Much faster. The Chicxulub asteroid was traveling at roughly 20 kilometers per second when it struck. The Tunguska object, entering almost vertically, was moving around 15 kilometers per second. 3I/Atlas is moving at 30 kilometers per second, and velocity matters enormously in impact physics because kinetic energy this comet carries is staggering. Let's put some numbers to this. The kinetic energy of a moving object equals 1/2 times its mass times its velocity squared. For 3I/Atlas, 100 million tons moving at 30 kilometers per second, that works out to approximately 45,000 megatons of energy. The largest nuclear weapon ever detonated, the Soviet Tsar Bomba tested in 1961, yielded 50 megatons. This single impact would release energy equivalent to 900 Tsar bombas detonating simultaneously in the same place. This is not science fiction. This is orbital mechanics, physics, and geology. We know these things happen because we've found the craters. We've analyzed the shocked minerals and melted rock. We've correlated mass extinctions with impact events. And we've watched impacts occur on other worlds. The question isn't whether objects from space can devastate a planet. The question is what happens when they do. What we're about to explore is the story of such a collision. Not the actual 3I/Atlas. That comet is long gone, safely back in the void where it spent 4 billion years. But an object like it carrying the same mass, moving at the same velocity, approaching from interstellar space with a trajectory that intersects Earth's orbit at precisely the wrong moment. This is the story of what would happen if that wanderer's 4 billion-year journey ended here, on our world, instead of sailing peacefully past. This is the story of a collision between two ancient histories, the 4.5 billion-year story of Earth, a planet that has survived countless impacts, mass extinctions and climate catastrophes, and the unknowably old story of a comet from beyond, a fragment of a failed solar system that traveled across light years to deliver destruction. The impact would last less than a second. The immediate effects would unfold over hours. The global catastrophe would develop over months. The recovery would take millennia, and the changes would be permanent, written into the planet's geology, its climate, its biology, and if any survived, into the evolutionary trajectory of every species, including our own. We have the mathematics to model this. We have supercomputers running simulations based on impact physics refined through decades of research. We have the geological record of previous impacts to calibrate our models against. We know with disturbing precision what would happen, and that knowledge is both terrifying and potentially our salvation, because understanding the threat is the first step toward preventing it. The comet from beyond carried no malice. It's just ice and rock, following the laws of physics across the cosmos. But physics doesn't care about intention. A comet moving at 30 kilometers per second carries enough kinetic energy to fundamentally alter the trajectory of life on Earth. Whether it would mean the end of humanity, the end of most species, or merely the end of civilization as we know it, depends on dozens of variables. Where it hits, the angle of impact, how much warning we have, how prepared we are. But before we can discuss prevention or preparation, we need to understand exactly what we'd be facing. We need to walk through the scenario step by step, moment by moment, consequence by consequence. We need to see the physics transform into fire and shockwave. Watch the local catastrophe become global. Observe the immediate destruction give way to long-term environmental collapse. And understand both the mechanisms of devastation and the potential pathways to survival. This is that story. This is what would happen if an interstellar visitor decided to stay. The comet enters Earth's atmosphere at 30 kilometers per second. Let's put that number into perspective, because it's difficult to grasp just how fast this really is. A rifle bullet travels about 1 kilometer per second, already faster than sound, fast enough that you can't see it coming. The space shuttle, when it re-entered Earth's atmosphere, was moving at roughly 8 kilometers per second, and that required elaborate ceramic heat shields and careful angle control to avoid burning up. 3 I/Atlas is moving nearly 4 times faster than the fastest human-made re-entry vehicle ever built. At this velocity, air itself transforms into a weapon. The moment the comet makes contact with the upper atmosphere, about 100 kilometers above the surface, physics takes over with brutal, unstoppable efficiency. Here's what's actually happening. The air molecules in front of the comet cannot move out of the way fast enough. They simply don't have time to flow around the object. Instead, they compress, and when you compress air, you generate heat. This is the same principle that makes a bicycle pump warm when you inflate a tire, but amplified to a degree that's almost impossible to comprehend. The temperature at the comet's leading edge reaches tens of thousands of degrees in a fraction of a second. The comet begins to glow, not with reflected sunlight, but with its own thermal radiation. It becomes brighter than the sun, visible across half the planet, even in broad daylight. People thousands of kilometers away look up to see a second sun blazing across the sky, growing brighter by the second. But here's the crucial thing. The atmosphere barely slows it down. For objects this size moving this fast, air might as well not be there. The comet plows through 100 kilometers of atmosphere in less than 10 seconds. That's all the time Earth has, 10 seconds from the moment it enters the atmosphere until impact. No warning sirens, no time to take cover. Just 10 seconds of terror as the sky lights up and the roar becomes deafening. Let's say it hits land, a continental impact. The mechanics of what happens next have been studied in laboratories where scientists use high-speed cameras to film projectiles striking targets at hypervelocity. They've been modeled in supercomputers running simulations of the physics involved, and they've been observed in the geological record of previous impacts, where the evidence is frozen in shocked minerals and melted rock. At 30 kilometers per second, solid matter behaves like fluid. This is one of those facts that challenges our everyday experience of how materials work. We think of rock as hard and solid, incapable of flowing. But that's only true at the speeds and pressures we normally encounter. At the velocities involved in cosmic impacts, rock flows like water, or more accurately, like a water droplet hitting a still pond. In the first microseconds, millionths of a second, the comet's leading edge compresses under the deceleration force, then vaporizes, releasing a shockwave that travels faster than sound through both the comet and the ground beneath it. The rock under the impact point doesn't crack or fracture in the way we normally think of rock breaking. It flows. It splashes upward and outward like that drop hitting a pond, except the water is granite and limestone, moving at supersonic velocities. Heated to temperatures that would melt steel in an instant, the kinetic energy of the impact, 100 million tons of mass moving at 30 kilometers per second, converts almost instantaneously to heat and pressure. We measured this energy earlier. Approximately 45,000 megatons. For comparison, the largest nuclear weapon ever detonated yielded 50 megatons. This single impact releases energy equivalent to 900 of those weapons detonating in the same place at the same moment. Within 1 second of impact, a fireball forms. This isn't fire in the chemical combustion sense, wood burning or gasoline exploding. This is thermal radiation so intense that it ionizes everything it touches, stripping electrons from atoms. The fireball expands to several kilometers in diameter, and its interior reaches temperatures found in stellar cores, 100,000 degrees Celsius. Everything within this sphere, rock, soil, water, any living thing, transitions instantly from solid or liquid to plasma, the fourth state of matter. The molecules that made up forests and cities and animals don't burn or melt. They cease to exist as molecules. Chemical bonds break. The matter becomes ionized atoms, suspended in a bubble of radiant energy. If the impact occurs near a population center, hundreds of thousands of people simply vanish, their bodies converted to plasma faster than nerve signals can travel. The shockwave follows immediately behind. It moves through rock at about 6 kilometers per second, faster than any earthquake wave ever measured. The shockwave carries more energy than the rock can structurally absorb. Granite, one of the hardest rocks on Earth, shatters like glass. Limestone pulverizes into powder. The ground itself becomes airborne, flung upward at velocities that carry it beyond the atmosphere. This is not a metaphor. Material from the impact literally reaches space. Millions of tons of vaporized and molten rock begin ballistic trajectories that will take them around the planet, into temporary orbit, or in some cases, escaping Earth's gravity entirely to become tiny satellites of the Sun. Some of this material will rain back down across the entire planet over the next several hours. Some will drift in orbit for days or weeks before spiraling back into the atmosphere. And some will simply leave Earth forever, carrying trace amounts of terrestrial geology into interplanetary space. By 10 seconds after impact, the crater is actively forming. Not through excavation, not by digging or drilling, but by displacement of unimaginable violence. The comet vaporized on contact, but its momentum transferred to the ground beneath it. Rock moves outward and downward, pushed by pressures exceeding 1 million atmospheres, 1 million times normal air pressure at sea level. The crater grows like a ripple spreading across a pond, except it's kilometers wide and carved into solid bedrock. The transient crater, the initial cavity before the walls become unstable and collapse, reaches approximately 10 kilometers in diameter and 3 kilometers deep. Picture a hole wide enough to swallow a medium-sized city, deep enough that if you stood at the rim, the bottom would be hidden in the haze of vaporized rock and superheated air. The walls of this crater are not solid. They're fractured, shattered rock, held together by nothing but momentum and inertia. Simultaneously, the atmosphere itself becomes a weapon. The impact generates what's called an air blast, a hemispherical shockwave of compressed air moving outward at supersonic velocity in all directions from ground zero. At the impact site, wind speeds exceed 1,000 kilometers per hour. This is not wind as we normally experience it. Trees don't bend and break. They vaporize from friction heating with the air. Buildings don't collapse. They atomize into constituent molecules. The shockwave races outward, weakening with distance according to well-understood physics, but remaining lethal for hundreds of kilometers. Then comes the thermal pulse, the second wave of destruction. The fireball, now 15 kilometers wide and still radiating at thousands of degrees, releases energy across the entire electromagnetic spectrum. Infrared radiation carries heat. Visible light carries more heat. Ultraviolet radiation carries even more energy, and all of it propagates outward at the speed of light, 300,000 kilometers per second. Anything with direct line of sight to the fireball ignites. This is the mechanism that would be most familiar to anyone who's focused sunlight through a magnifying glass, but amplified beyond comprehension. Wood bursts into flame spontaneously at distances of hundreds of kilometers. Clothing catches fire on people standing 500 kilometers away, far beyond the horizon. But elevated positions or atmospheric effects can provide line of sight. Exposed skin receives third-degree burns at 800 kilometers. The thermal pulse lasts about 20 seconds, long enough to ignite continental-scale firestorms that will burn for days. By 1 minute after impact, the dynamics shift dramatically. The crater walls, pushed far beyond their structural limits, begin collapsing inward. Millions of tons of fractured rock slide back toward the center, partially filling the cavity in a process that takes several more minutes. The collapse generates another set of shock waves, both through the ground and through the air, like aftershocks from an earthquake, except more powerful than the initial quake would have been for any natural tectonic event. Meanwhile, the ejecta, the material thrown upward by the impact, is falling back to Earth. But it's not falling cold. Friction heated it to incandescence on the way up, essentially converting it into thousands of meteors. Now these glowing fragments re-enter the atmosphere across thousands of kilometers, each piece depositing its kinetic energy as heat, each one capable of starting fires wherever it lands. The sky becomes a meteor shower of such density that night turns to day across half the planet. The ground shakes globally. Seismometers on the opposite side of the planet, 12,000 kilometers away, register the impact as a magnitude 9.5 earthquake, equivalent to the largest earthquake ever recorded by instruments, the 1960 Chilean quake. But impact-generated seismic waves differ fundamentally from earthquake waves. They carry more high-frequency energy, traveling through rock with a sharp, shattering quality rather than the rolling motion of tectonic earthquakes. Faults slip worldwide. Every fault line on the planet that was already under stress, already near the point of failure, suddenly finds that stress exceeded. The impact seismic waves act like a trigger, releasing accumulated tectonic tension in locations scattered across the globe. Mountains shed rockslides, unstable slopes fail. Coastal regions experience ground liquefaction, where saturated soil behaves like fluid. Coastlines slump into the sea, generating local tsunamis independent of any direct water displacement from the impact. If the impact occurs in ocean rather than on land, the immediate mechanics change, but the energy remains the same. The water above the impact point vaporizes instantly, flash-boiled into steam by temperatures exceeding 10,000 degrees. For a brief moment, there's a cavity in the ocean, a hole in the water where the ocean floor has been exposed and cratered. But water, unlike air, carries momentum effectively. The ocean floor beneath the impact behaves exactly like land would. It craters, it fractures, it displaces, and in displacing it moves the entire water column above it. A tsunami forms, but not like any tsunami generated by an earthquake. Impact tsunamis are fundamentally different phenomena. The initial wave height at the impact site exceeds 1 kilometer, a wall of water taller than the tallest skyscraper ever built, moving at speeds approaching that of a commercial jet aircraft. This wave carries energy that will cross entire ocean basins without significant dissipation. It races outward in all directions, a circular wave front carrying destruction to every coastline within range. By 1 hour after impact, the immediate destruction zone is established and largely static. Everything within 500 kilometers of ground zero is gone, vaporized, incinerated or crushed by the shockwave. There are no survivors in this zone. There are no ruins. There is only a landscape of melted and shattered rock, still glowing red-hot in many places, overlaid with a thin coating of material that's fallen back from space. From 500 to 1,000 kilometers, nothing survives above ground. Buildings are rubble, forests are charcoal. The shockwave's passage left nothing standing. Underground structures might remain intact, basements, subway tunnels, natural caves, but everything on the surface has been destroyed. People who were in underground spaces when the shockwave passed might survive the initial blast, but they emerge into a moonscape where every landmark has been erased. From 1,000 to 2,000 kilometers, destruction is selective but widespread. The shockwave has weakened to the point where some structures survive while others fail, depending on their construction and orientation to the blast. Fires rage everywhere, started by the thermal pulse and spreading unchecked in the chaotic aftermath. Windows shattered by the pressure wave have injured millions. Buildings not designed for seismic loads have collapsed. The infrastructure of modern civilization, power lines, water mains, communication networks is comprehensively damaged. But this first hour, devastating as it is, represents only the local catastrophe. What follows is something far worse, the global catastrophe that will unfold over months and years. Already high in the stratosphere, the mechanisms of worldwide devastation are beginning. The plume from the impact, carrying millions of tons of pulverized earth, has punched through the entire atmosphere. It's created a column of ejecta that extends into space, a mushroom cloud visible from the International Space Station if anyone there is still alive to observe it. Most of this material is falling back, but not all of it. The finest particles, just microns across, are being lofted into the stratosphere by the updrafts of heat and by their own momentum. The stratosphere is stable, unlike the troposphere below it, where weather happens, where rain and snow wash particles out of the air. The stratosphere is calm. There's no precipitation up there to cleanse the air. Dust injected into the stratosphere stays there, suspended, slowly spreading around the planet on high-altitude winds. These particles will block sunlight. They will change the climate. They will trigger a cascade of ecological collapse that will kill more than the impact itself. The first hour established the destruction zone. What comes next will determine whether human civilization, and perhaps humanity itself, has a future. The comet's journey took 4 billion years. The impact lasted less than 1 second, but the consequences will unfold over timescales measured in generations, if there are any generations left to measure them. 6 hours after impact, and the disaster is mutating into something far more complex than a simple explosion. The initial impact was geographically limited, catastrophic within its zone, absolutely, but confined to a region measured in thousands of kilometers. Now the secondary effects begin, and they respect no boundaries. The ejecta is falling across distances that span continents. Remember those millions of tons of material thrown into space? Every piece that went up is coming down, and each piece is a projectile moving at orbital velocities, several kilometers per second. The sky fills with meteors, so many that the night side of the planet glows with their collective light. If you could see the entire planet from space, it would look like Earth is surrounded by a sparkling shell of incandescent material spiraling back into the atmosphere. Each returning fragment generates heat through friction with the air. The smaller pieces, gravel-sized and smaller, burn up completely, but in doing so they deposit their kinetic energy into the upper atmosphere, heating it by hundreds of degrees. This has never happened in human history. The upper atmosphere is warming dramatically, and this warming will affect weather patterns and atmospheric circulation in ways that are difficult to predict, but certainly disruptive. The larger fragments survive their fiery passage through the atmosphere and strike the ground. Each impact is a small explosion. A boulder-sized piece, hitting at several kilometers per second, releases energy equivalent to tons of TNT. Thousands of these secondary impacts are occurring across vast areas, and each one starts fires, and fires are spreading with terrifying speed. The thermal pulse ignited everything flammable within line of sight of the fireball 6 hours ago. Those initial ignition points, millions of them, scattered across thousands of square kilometers, have merged into firestorms. This is where we need to understand the physics of firestorms, because they're self-sustaining disasters that create their own weather. Fire creates heat. Heat creates updraft. Hot air rises. The updraft draws in surrounding air from all directions to replace the rising hot air. This incoming air carries oxygen, which feeds the fire, which creates more heat, which creates stronger updraft, which draws in more air. It's a positive feedback loop, and once it's established, it becomes almost impossible to stop. The firestorms generate winds strong enough to uproot trees, not from the shock wave, but from the circulation pattern of the fire itself. These winds draw more fuel into the flames. Embers carried by the wind start new fires kilometers downwind. The convection from the fires is so powerful that it creates pyrocumulonimbus clouds, fire-generated thunderstorms that tower 20 kilometers into the sky. These clouds generate lightning that starts yet more fires in areas that hadn't yet been burning. The physics of firestorms was tragically learned during World War II in the bombing of Hamburg, Dresden and Tokyo, and later in the atomic bombings of Hiroshima and Nagasaki. Military planners discovered that under certain conditions, enough fires started simultaneously would merge into a firestorm that was more destructive than the bombs themselves. What we're witnessing now is firestorms on a continental scale, and they will burn for days. If the impact hit ocean instead of land, 6 hours gives the tsunami time to cross entire ocean basins. At 800 kilometers per hour, the speed of a commercial jet, the wave has traveled nearly 5,000 kilometers. It's approaching coastlines on multiple continents simultaneously. Here's what's crucial to understand about tsunami propagation. In deep ocean, the wave is barely noticeable. A ship in deep water might experience a few meters of rise spread across hundreds of kilometers of wavelength. They'd notice their instruments showing unusual readings, but they wouldn't see or feel anything dramatic. The wave's energy is distributed throughout the entire water column, from surface to seafloor, which in deep ocean might be 4 or 5 kilometers deep. But as the tsunami approaches shore and the water becomes shallower, the entire energy budget of the wave compresses vertically. The wave's front edge enters shallow water first and slows down. Friction with the seafloor robs it of speed. But the back of the wave is still in deep water, still moving at full speed. The back catches up with the front and the wave grows taller. By the time it reaches shore, the leading edge is 50 to 100 meters high, a moving cliff of water carrying everything it collected while crossing the ocean. Coastal cities have perhaps 15 to 30 minutes of warning from the time the wave becomes visible on the horizon until it strikes. Evacuation is physically impossible on that timescale. You cannot move millions of people to high ground in half an hour. The people watching from coastal areas see something approaching that looks like the ocean itself has risen up and is advancing toward land. The wave doesn't break like a surfing wave, curling over and crashing down. Instead, it surges, a rapid rise in sea level that continues advancing inland like a wall of water moving forward. The water travels kilometers from shore, carrying ships, buildings, vehicles, trees, everything it encounters, in a churning slurry of debris that gains mass and destructive power as it moves. When the wave finally exhausts its energy and begins receding, it drags everything back to sea. Survivors who made it to upper floors of strong buildings find themselves suddenly surrounded by retreating water, carrying the debris of entire cities. And then the second wave arrives, then the third. Impact tsunamis generate wave trains that continue for hours, each successive wave arriving to find the landscape already devastated, ready to tear away whatever remained after the previous surge. 12 hours after impact, the atmospheric dynamics are becoming clear and deeply troubling. The explosion punched a hole through the atmosphere, a temporary vacuum that is now collapsing. Basic physics: air moves from high pressure to low pressure. The impact created the ultimate low-pressure system at ground zero, and now air is rushing back toward the impact site from all directions. This creates surface winds of 100 kilometers per hour, extending thousands of kilometers from the impact point. These winds are sustained, not gusts. They blow steadily for hours, and they feed the firestorms. Fires that might have burned themselves out in calm conditions instead spread exponentially, driven by these convergent winds into wildfires that race across continents faster than animals can flee. The dust plume is spreading with mathematical precision. High-resolution computer models of impact dynamics show exactly how this works. The finest ejecta, particles smaller than 10 microns, about 1/10 the width of a human hair, are lofted into the stratosphere where they're caught by high-altitude winds. These winds, called the stratospheric jets, circle the Earth at altitudes of 30 to 50 kilometers. The stratosphere is stable. This is crucial to understanding what comes next. In the troposphere, the lowest layer of atmosphere where we live and where weather occurs, air moves vertically. Hot air rises, cold air sinks, moisture condenses and falls as rain or snow. This vertical mixing cleanses the troposphere of particles relatively quickly. But in the stratosphere, there's no vertical mixing. The air forms stable layers. There's no weather up there to wash particles out. Dust injected into the stratosphere stays there. It spreads horizontally around the planet on those stratospheric winds, but it doesn't fall out quickly. The plume begins circumnavigating the equator, a brown haze visible from space, spreading latitudinally as it circles. Within 24 hours, it will encircle the entire planet. Within a week, it will cover all latitudes, and it will remain there for months or years, depending on particle size. Sunlight striking this dust scatters and absorbs. The particles act like a screen between the sun and Earth's surface. Less light reaches the surface. The dimming begins. 18 hours after impact, the ecological collapse is starting, and it's starting with plants. Photosynthesis responds to light on cellular timescales, minutes to hours. Plants are exquisitely sensitive to light intensity because their entire existence depends on converting sunlight into chemical energy. Across the hemisphere facing the impact, photosynthesis is already declining as airborne dust reduces illumination. The effect starts small, a 10% reduction in light intensity barely noticeable to human eyes. But to a plant operating at the margins of energy efficiency, 10% less light means 10% less sugar production, and plants have fixed energy costs for cellular maintenance. The equation starts to tip negative. It's global, and it's accelerating as more dust enters the stratosphere with each passing hour. Plants can tolerate brief darkness. They do it every night. Their cells have mechanisms for surviving until sunrise. But this darkness won't end with sunrise. When dawn comes 18 hours after impact, the sun rises pale and dim, filtered through a thickening veil of dust. The seismic effects continue, cascading in ways that are predictable given what we know about earthquake triggering. The impact generated stress waves that traveled through the entire planet, ringing it like a bell struck by a hammer. These waves carried enough energy to trigger earthquakes along fault lines that were already near failure, faults that might have slipped tomorrow or 10 years from now, but were pushed over the edge by the impact's seismic energy. The 1960 Chilean earthquake, magnitude 9.5, the largest ever recorded by instruments, triggered earthquakes worldwide. That was natural tectonic movement, the sudden slip of one tectonic plate past another. The impact delivers far more energy far more suddenly, and it triggers faults from Alaska to New Zealand, from California to Japan. Each earthquake generates aftershocks, smaller quakes as the fault continues adjusting to its new configuration. Aftershocks trigger landslides. In mountainous terrain, slopes that were stable before the shaking now fail, sending millions of tons of rock and soil sliding into valleys below. Coastal landslides generate their own local tsunamis, independent of the main impact tsunami. These local waves are smaller, but can be devastating to nearby coastal communities already dealing with the aftermath. Volcanic regions respond, though not in the way movies might suggest. The impact didn't cause eruptions. That's not how volcanoes work. You can't simply shake magma to the surface. But what the stress waves did do was affect magma chambers that were already under pressure, already close to erupting. Gas-rich magma chambers on the edge of erupting are pushed over the threshold. Within 24 hours, dozens of volcanoes show increased activity. Some erupt, adding volcanic ash to the atmospheric burden of impact dust. The ash is compositionally different. Sharp fragments of volcanic glass rather than pulverized rock, but the effect is the same. More particles blocking sunlight, more aerosols in the stratosphere, more reasons for the planet to cool 24 hours after impact, and the immediate crisis is established across the entire planet. The destruction zone, 2,000 kilometers from impact, contains only ruins and corpses. Everything that could burn has burned or is burning. Smoke columns tower into the stratosphere, carrying soot that's even more effective at blocking sunlight than mineral dust. Beyond the destruction zone, buildings still stand, but infrastructure is failing. Power grids were designed with redundancy to handle local failures. A downed line here, a failed transformer there. But they weren't designed for global simultaneous damage. The seismic shaking damaged generation plants. The fires destroyed transmission lines. The electromagnetic pulse from the impact, created by the ionization of the atmosphere, damaged electronic control systems. The grid is collapsing region by region, as isolated sections run out of fuel or protective systems shut them down. Communication networks face similar cascading failures. The internet was designed to route around damage, with multiple paths between any 2 points. But all the backup paths failed simultaneously. Undersea cables were cut by the tsunami. Satellite ground stations were destroyed. The atmosphere is so ionized by the impact and the ongoing re-entry of ejecta that radio communications are disrupted. Emergency broadcasts paint a picture of global crisis, but the broadcasts are reaching fewer and fewer receivers as power fails. The atmospheric burden is now measurable worldwide with simple instruments. Sunlight at the surface is reduced by 20% compared to normal, a change obvious to anyone who looks at their shadow or measures it with a light meter. Temperatures are dropping, not dramatically yet, just a few degrees, but the trend is clear and accelerating. Weather patterns are disrupting as the temperature gradient between equator and poles weakens. Normally, tropical regions receive more sunlight and are warmer. Polar regions receive less and are colder, and this temperature difference drives atmospheric circulation. Warm air rises at the equator, flows toward the poles at high altitude, sinks in polar regions, and returns toward the equator at the surface. This circulation creates the trade winds, the jet streams, the patterns of rainfall and drought that define Earth's climate zones. Now the tropical regions are receiving less sunlight. They're cooling. The temperature gradient is weakening. The atmospheric circulation is slowing down. Weather systems that would normally move, carried by the jet stream or trade winds, are stalling in place. Storms that would normally pass in days instead persist for weeks, dumping rain or snow on the same regions continuously. Ocean systems are responding on their own timescales. The impact's seismic waves generated vibrations in the water column that killed fish by the billions. The shockwave ruptures swim bladders, the gas-filled organs that fish use to maintain buoyancy, and causes internal hemorrhaging. Dead fish float to the surface in masses that extend thousands of kilometers from the impact point, creating a biological catastrophe visible from space. The die-off removes a key link in marine food chains. Predators that depend on fish, seabirds, marine mammals, larger fish, face starvation within days. Seabirds that should be fishing are instead floating on the surface, starving, unable to find prey. Dolphins and whales, intelligent animals capable of recognizing the catastrophe unfolding around them, search desperately for food in waters suddenly devoid of their normal prey. Human civilization is fragmenting under stresses it was never designed to handle. Modern civilization is incredibly efficient but remarkably fragile. Efficiency means eliminating redundancy, running systems at near capacity, depending on just-in-time delivery of supplies. This works beautifully during normal operations, but fails catastrophically when disrupted. The initial impact destroyed regions and killed hundreds of millions in the immediate destruction zone. The global infrastructure damage, ports destroyed, shipping routes disrupted, power grids failed, has isolated regions that once traded freely. A factory in one country depends on parts from another country, and those parts are no longer arriving. A city depends on food imports from agricultural regions, and the trucks and trains aren't running. Emergency broadcasts, where they're still functioning, paint a picture of global crisis. The immediate destruction zone is silent, all infrastructure destroyed, all communications cut. Surrounding regions report building collapses, fires, casualties in millions. Coastal areas report tsunami damage, harbors destroyed, fleets sunk. The global scope becomes clear. There is no safe zone to evacuate to, no unaffected region that can send aid. Every region faces its own crisis simultaneously. The first day ends, not with a bang, but with a terrible dawning realization. The immediate destruction killed millions, but the dust blocking sunlight, the fires pumping soot into the stratosphere, the disrupted ocean circulation, the damaged infrastructure, these guarantee that the disaster has only begun. The planet is entering a new phase, one that will last not hours but months and years. Impact winter is beginning. And winter, as they say, is coming. 1 week after impact, the sun rises dim and red across the planet. Everywhere, from equator to poles, daylight has the quality of late twilight. The dust veil, now distributed globally by stratospheric winds, blocks 40% of incoming solar radiation. To understand what this means, we need to look at how the effects ripple through every system on Earth. Plants notice first because their survival depends entirely on photosynthesis, and photosynthesis is an exquisitely tuned process. It evolved over billions of years under Earth's specific light intensity and spectrum. Every species of plant is adapted to a certain range of light conditions. Reduce the light by 40%, and photosynthetic efficiency collapses in ways that aren't linear. Here's what's really happening at the cellular level. Plants don't simply produce 40% less sugar when light drops by 40%. Below certain light thresholds, the energy cost of maintaining cellular machinery exceeds the energy gained from photosynthesis. The plant operates at a deficit, consuming its stored reserves, starches in roots, sugars in stems, just to keep its cells alive. It's like running a business where expenses exceed income. You can survive for a while on savings, but eventually you go bankrupt. Within 2 weeks, observable changes appear worldwide. Deciduous trees in temperate regions, already stressed by the sudden temperature drop, begin shedding leaves out of season. This is an emergency response hardwired into their biology. Reduce surface area, reduce energy consumption, go dormant. It's the same response triggered by autumn, but autumn usually comes gradually, giving trees time to move nutrients from leaves back into wood and roots. This emergency shedding is wasteful, inefficient, but necessary for survival. Evergreen trees like pines and firs face a different problem. They cannot shed needles quickly. Their needles are designed to persist for years, weathering winter and continuing photosynthesis whenever conditions allow. Now those needles, unable to photosynthesize efficiently in the dim light and stressed by the sudden cold, begin browning and dying while still attached to branches. The trees persist longer than deciduous trees, but they're suffering more damage. Agricultural crops, designed by 10,000 years of selective breeding for maximum yield rather than hardiness, fare worst of all. Fields of corn and wheat, only weeks from harvest in some regions when the impact occurred, wither in the dim, cold conditions. The grain never matures. The investment of water, fertilizer, and labor that went into planting these crops is lost. And this is happening globally, simultaneously, in every agricultural region on Earth. 1 month after impact, the global average temperature has dropped 5 degrees Celsius. 5 degrees may not sound dramatic. It's the difference between a comfortable day and a chilly day. But averaged globally and sustained for months, it transforms everything. The mechanism is straightforward. Less sunlight reaches the surface, so less energy enters the climate system. Earth's climate is fundamentally an energy budget. Energy comes in from the sun, gets absorbed by land and ocean, and radiates back to space as infrared. When you reduce the incoming energy, Temperature drops until a new equilibrium is reached, where incoming energy again balances outgoing energy. The temperature drop is not uniform across the planet. Coastal regions, moderated by the ocean's enormous thermal mass, water stores heat far more effectively than air or land, cool slowly. The oceans act as a buffer, releasing stored heat and slowing the temperature decline. Continental interiors, lacking that buffer, cool rapidly. Northern latitudes, already receiving less sunlight even under normal conditions, cool dramatically. The Arctic Ocean, which normally remains ice-free during summer, begins freezing in May, months before it should. The crop failure becomes global within 6 weeks. Modern agriculture is finely tuned to temperature and light conditions through centuries of crop development and decades of scientific breeding. Each crop variety has optimal ranges for temperature, day length, water, and light intensity. Outside those ranges, yields drop precipitously or fail entirely. Wheat requires specific day lengths to trigger flowering. Too short and it remains vegetative, too long and it bolts prematurely. Corn requires accumulated heat units to mature. The plant essentially counts warm days until it has enough to produce grain. Rice requires flooded paddies, maintained at specific temperatures for the right duration. All these conditions are disrupted simultaneously worldwide. The spring planting in the northern hemisphere never germinates in the dim, cold conditions. Seeds that require soil temperatures above a certain threshold to sprout find the soil too cold. Those that do germinate find insufficient light for growth. The growing crops in the southern hemisphere fail to mature. Plants that are halfway through their growth cycle when the impact occurs simply stop growing, unable to photosynthesize efficiently, and eventually die. The food crisis begins not with famine, but with logistics and mathematics. Modern civilization doesn't store large food reserves because storage is expensive and food spoils. Instead, we depend on continuous production and just-in-time distribution. Supermarkets maintain 3 days of inventory. Regional warehouses hold perhaps 2 weeks. Strategic reserves in some nations hold 3 to 6 months of staple grains, but most nations don't even have that. The mathematics is straightforward and brutal. With crops failing globally, stored food must feed 7 billion people with no prospect of new harvests. Assuming perfect distribution, which absolutely won't happen, global food reserves last 3 to 4 months. In reality, distribution is anything but perfect. The infrastructure damage from the impact has disrupted transportation networks. Fuel for trucks and ships is increasingly scarce, and nations with reserves aren't sharing them. 2 months after impact, the first mass starvation begins. It doesn't start everywhere simultaneously. It starts in regions that were already food insecure, that depended on imports, that lacked strategic reserves. Sub-Saharan Africa, parts of South Asia, island nations, anywhere that normally imports more food than it produces faces immediate crisis. The distribution networks, already damaged by the initial impact and its aftereffects, cannot move food from areas of surplus to areas of need. Ports are damaged or destroyed. Container ships that survived the tsunami sit idle because loading equipment doesn't work or because there's no fuel. Shipping routes are disrupted. Fuel for transportation becomes increasingly scarce as refineries shut down, some damaged directly, others unable to operate because they can't get crude oil imports. The ecological collapse follows the energy pyramid with remorseless logic. Photosynthesis is the base of nearly all food chains on Earth. When primary productivity collapses, everything built on top of it collapses upward through each trophic level. Herbivores run out of food first. Deer in forests where browse has died are starving by the thousands. Cattle in fields where grass has browned stand listlessly, their ribs showing through their hides. Wild herbivores evolved to survive harsh winters, but not global winters, where no food exists anywhere within their range. Domestic herbivores depend on humans to feed them, and humans have no feed to give. The herbivores die over a period of weeks, their bodies consuming themselves in a desperate attempt to survive. Metabolism breaks down muscle tissue to keep vital organs functioning. Fat reserves deplete. The immune system weakens. Disease spreads through weakened populations. Eventually, the heart lacks the energy to beat, and they die. Billions of them worldwide, simultaneously. Predators follow with a brief delay. Wolves and bears, hunting herbivores, find prey increasingly scarce but initially easier to catch. The starving herbivores are weak and slow. For a brief period, predators feast. But the prey population is finite, and no new young are being born. The predators themselves face starvation within months. Scavengers experience a boom and bust cycle. Species that eat carrion, vultures, hyenas, crows, insects, find unlimited food in the billions of corpses. Scavenger populations explode, but they're consuming a non-renewable resource. Within months, the corpses are gone, and the swollen scavenger populations face starvation themselves. Vultures that numbered in the thousands now number in the tens, and those survivors face a landscape devoid of food. Ocean ecosystems collapse differently, but just as thoroughly. The impact killed billions of fish immediately through shockwave trauma. We discussed that earlier. Now the survivors face their own crisis. Marine food chains start with phytoplankton, microscopic photosynthetic organisms that drift in the sunlit surface waters. They're essentially underwater plants, and like terrestrial plants, they need light. In deep ocean waters, far from the impact site and far from the turbidity caused by the tsunami, phytoplankton populations are declining but not yet collapsing. They can survive on reduced light for a time. In shallower coastal waters, stirred by the tsunami and clouded with sediment, the die-off is near total. No light penetrates the turbid water. No photosynthesis occurs. The phytoplankton die. Zooplankton, tiny animals that eat phytoplankton, starve next. They're the key link between primary producers and everything larger. Larval fish depend on zooplankton as their first food. Adult fish of many species eat zooplankton directly. Baleen whales filter zooplankton by the ton. When zooplankton populations crash, the entire marine food web fractures. Fish populations collapse within a single generation, which for many species is mere months. The fish that survived the initial impact and its immediate effects now find no food. Spawning occurs. It's triggered by seasonal cues that don't know the world has changed, but the larvae that hatch find no zooplankton to eat. They starve within days. The fish population becomes entirely adult fish, and those adults are starving. 3 months after impact, and the temperature has dropped 8 degrees Celsius globally. Northern Hemisphere winters are 15 degrees colder than normal. Southern Hemisphere summers feel like mild springs at best. This temperature shift is enough to fundamentally alter weather patterns and precipitation. Precipitation patterns have shifted drastically, and here's why. The reduced temperature gradient between equator and poles weakens atmospheric circulation. The Hadley cells, the circulation pattern where air rises at the equator, flows toward the poles at high altitude, sinks around 30 degrees latitude, and returns toward the equator at the surface, are weakening. The jet streams driven by temperature gradients meander erratically. Weather systems stall because they're no longer being pushed along by strong jet stream winds. Storms that would normally pass through a region in days instead persist for weeks. Monsoons fail because they depend on temperature differences between ocean and land to drive the seasonal winds that bring rain. Regions that depend on those seasonal rains receive none. The regions experience endless storms, dumping snow in the northern hemisphere and cold rain in the southern. The water cycle itself is disrupting. Normally, the sun evaporates water from oceans and surface waters. The vapor rises and condenses into clouds, and precipitation falls. With 40% less sunlight, evaporation has dropped dramatically. But the water already in the atmosphere still precipitates. This imbalance shifts weather patterns in unpredictable ways. Some regions experience drought despite global cooling. Others flood from precipitation that no longer evaporates to be recycled. Human civilization fractures under compound stresses that interact and amplify each other. The initial impact destroyed regions and killed hundreds of millions. That was the immediate crisis. The global infrastructure damage isolated regions that once traded freely. That was the secondary crisis. Now the crop failure and food crisis push every remaining population toward collapse. This is the tertiary crisis, and it's the one that will determine humanity's survival. Nations with reserves implement rationing, distributing stored food through government channels to make supplies last as long as possible. But rationing only delays the inevitable. The mathematics of millions of people consuming food with no new production has only one outcome. The reserves run out. Social order degrades differently in different regions, depending on governance, social cohesion, and resource availability. Some governments maintain control through force, implementing martial law, requisitioning all food supplies for central distribution, and suppressing dissent with military power. This works, after a fashion, until the soldiers themselves start starving. Other regions collapse into chaos as desperate populations fight over dwindling resources. Grocery stores are looted within days. Government food distribution centers become riot zones. People flee cities, concentrations of millions, with no local food production, hoping to reach rural areas where food might exist. But rural areas are equally stricken. The farms that normally fed cities are producing nothing. 4 months after impact, midwinter in the northern hemisphere, temperatures are holding at 10 degrees below normal. Snowpack accumulates to record depths. Rivers freeze solid, shutting down hydroelectric power plants and cutting off water supplies to cities that depend on river water. Coastal waters develop sea ice that extends far beyond normal limits. The Mediterranean Sea, which normally never freezes, develops ice at its northern edges. The Black Sea becomes an ice shelf. These are conditions not seen in thousands of years, conditions that modern ecology and infrastructure are completely unprepared for. Pipes burst, roads become impassable. Heating systems designed for normal winters cannot cope with temperatures this extreme, sustained for months. 6 months after impact, humanity faces its greatest test since the species evolved. The global population, 7 billion before impact, has fallen to perhaps 4 billion. Most deaths are from starvation. The food simply ran out and people died of hunger. Many more deaths come from disease. Malnutrition weakens. Immune systems and disease spreads rapidly through weakened populations lacking medical care. Others die from cold. Without power for heating, without fuel for fires, people in northern latitudes freeze. The elderly and very young die first, their bodies unable to maintain core temperature. Then the sick and malnourished. Eventually, even healthy adults succumb to hypothermia in unheated buildings during months of sub-zero temperatures. Violence accounts for a significant fraction of deaths. As resources dwindle, people fight over what remains. Some deaths are individual, murder over food or shelter. Others are organized, armed groups controlling resources and defending them from desperate outsiders. Entire communities are wiped out in conflicts over the last remaining food stores. The survivors cluster around resources. Military bases with strategic food reserves become fortified compounds. Government bunkers designed for continuity of operations during nuclear warhouse remnant authorities. Private bunkers shelter the wealthy and well-connected. Research stations in remote locations carry on with their stored supplies, isolated from the chaos elsewhere. Yet the darkness will not last forever, and this is crucial to understand. The dust in the stratosphere is settling, slowly but inevitably. Particles suspended in air eventually fall, pulled by gravity, however weak that pull might be for particles measured in microns. The largest particles settle first, within weeks. Medium-sized particles settle over months. The finest particles stay suspended for years, but even they settle eventually. Computer models run before the impact. Simulations designed to understand nuclear winter scenarios predicted the timelines with reasonable accuracy. The worst of the darkness, 70% of sunlight blocked, lasted about 6 months. Now 1 year after impact, sunlight reaching the surface has increased to approximately 60% of normal. It's still dim, perpetual twilight at noon, but it's improving. Temperature has stabilized at 6 degrees below pre-impact normal. It's cold, much colder than before the impact, but it's no longer dropping. The planet has found a new equilibrium point. The energy coming in from the reduced sunlight now balances the energy radiating back to space. This new equilibrium is colder than the old one, but it's stable. The ecological collapse has reached its nadir, its lowest point. The populations that could die have died. Those that remain are survivors selected by this catastrophe for their ability to tolerate darkness, cold, and scarcity. These remnant populations scattered across the planet represent the seed stock from which recovery will eventually emerge. The planet sits at a turning point. Behind lies the cascading destruction, the impact, the fires, the darkness, the cold, the starvation, the die-off of billions. Ahead lies recovery. Not a return to what was, but a slow reconstruction, a gradual healing, an evolutionary response to new conditions. Impact winter is ending. The worst is over. But the planet emerging from this catastrophe is fundamentally changed. The survivors face a world that's colder, darker, and emptier than the one they knew. The long process of recovery is about to begin. Deep beneath Earth's surface, nothing changed. 3 kilometers down in a South African gold mine, a colony of bacteria called Desulforudis audaxvieta lives in complete isolation from the surface world. These bacteria were discovered in 2008, and their existence revolutionized our understanding of life's possibilities. Here's what makes them remarkable. They don't need sunlight. They don't care about sunlight. They've never experienced sunlight in their entire evolutionary history. Their energy comes from radioactive decay of uranium in the surrounding rock. The radiation breaks down water molecules trapped in the rock, creating hydrogen, and the bacteria consume that hydrogen. They've lived this way for millions of years, completely isolated from the surface biosphere. When the impact occurred, when the shock wave rippled through the planet's crust, when the surface temperature plummeted and the sky went dark, Desulforudis noticed nothing. To them, the greatest catastrophe in millions of years was completely irrelevant. 3 kilometers of rock insulated them from every surface effect. They continued living exactly as they had before, thriving in conditions that would kill virtually any other organism on Earth. 2.5 kilometers beneath the ocean surface, at hydrothermal vents in the mid-Atlantic ridge, entire ecosystems flourish in complete darkness. These communities were discovered in 1977 by scientists in the submersible Alvin, and the discovery fundamentally changed biology. Until that moment, we believed all life on Earth ultimately depended on photosynthesis. These ecosystems proved us wrong. The vent communities depend on chemosynthesis, bacteria that harvest energy from hydrogen sulfide in the superheated water spewing from Earth's crust. These bacteria form the base of a food chain completely independent of sunlight. Tube worms 3 meters long absorb the bacteria and provide them with hydrogen sulfide, creating a symbiotic relationship. Blind shrimp graze on bacterial mats. White crabs scavenge whatever falls to the seafloor. The impact's shock waves pass through the ocean above them. In fact, if the impact had been oceanic, the shock waves would have been even stronger in the water. But down at the vents, protected by kilometers of water, and located near the heat of Earth's interior, these communities persisted. The surface catastrophe was distant and abstract. Down here, in the permanent darkness of the deep ocean, nothing changed. Arctic and Antarctic regions offered unexpected refuge, and this reveals something profound about adaptation. Organisms living at the poles already endure months of darkness every year during polar night. Emperor penguins breed during Antarctic winter, incubating eggs and raising chicks in temperatures of -40 degrees Celsius for 60 days without sunlight. They're adapted to darkness and extreme cold. When impact winter brought these conditions globally, polar species faced environments they already knew how to survive. The temperature dropped further at the poles, yes, but not as dramatically. Everywhere else was cooling to meet them. The marine mammals, seals, walruses, whales that hunt in polar waters found their range expanding. Fish populations, fleeing toward colder water as temperate zones cooled, migrated into polar regions where predators were waiting. In caves worldwide, ecosystems persisted untouched by the surface catastrophe. Cave-adapted species evolved in permanent darkness, many losing eyes entirely over millions of years because eyes serve no purpose in absolute darkness. They navigate by touch, by sensing vibrations in water, by detecting chemical gradients. These species depend on food sources independent of photosynthesis. Some eat bat guano, the droppings of bats that do venture to the surface but roost in caves. Others consume organic material washed in by underground rivers. Still others depend on chemosynthetic bacteria, similar to those at hydrothermal vents. The caves maintain constant temperatures year-round, insulated by rock from surface conditions. Whether the surface is experiencing summer heat or winter cold, or impact winter, makes no difference 50 meters underground. Cave salamanders that haven't seen sunlight in their entire evolutionary history didn't notice when the sun dimmed above. Cave fish that hunt by sensing electrical fields found their world completely unchanged. The deep soil harbored countless survivors, and this is easy to overlook because we think of soil as surface. But soil extends deep. Below the frost line, depth varies by latitude, but typically 1 to 3 meters. Soil temperature remains relatively stable. The daily and seasonal temperature swings that affect the surface barely penetrate to these depths. Root systems, tubers, seeds, and billions of microorganisms persisted in this refuge. Many plants evolved strategies specifically for surviving catastrophe. Deep storage roots can survive years underground without photosynthesis, living off stored starches. Seeds can remain dormant for decades or even centuries, waiting for favorable conditions. Some seeds actually require harsh conditions, fire or freezing, to break dormancy and germinate. When the surface froze and the plants above died, their below-ground structures often survived. Protected by soil, insulated from the temperature extremes, these survivors waited, and when conditions eventually improved, they would form the foundation for regrowth. Extremophiles, organisms that thrive in conditions we consider extreme, barely noticed the crisis. Tardigrades, microscopic animals also called water bears, represent perhaps the most resilient complex organisms on Earth. They can survive exposure to space, to radiation doses that would kill any other animal, to pressure extremes from vacuum to 6 times the deepest ocean, and to temperatures from near absolute zero to 150 degrees Celsius. Their survival strategy is cryptobiosis, essentially suspending all metabolic activity. A tardigrade in cryptobiosis isn't alive in the traditional sense. It's not metabolizing, not growing, not reproducing. But it's not dead either. It's waiting. When favorable conditions return, it rehydrates and resumes normal activity within hours. During impact winter, tardigrades in soil and moss worldwide simply went dormant. They'd done it countless times before during local droughts, during winter freezes, during summer heat waves. From their perspective, this was just another period of unfavorable conditions. They would wait it out, as they'd waited out unfavorable conditions for 500 million years. Hot springs and geothermal areas maintain stable temperatures independent of surface conditions. At Yellowstone National Park, Grand Prismatic Spring held steady at 70 degrees Celsius, while the air temperature plummeted to -20. The thermophilic bacteria that color the spring in brilliant oranges and greens, organisms that live at temperatures that would cook most life, experienced no disruption. These bacteria are adapted to heat, not cold, but the heat they depend on comes from geothermal energy, not sunlight. Similarly, hot springs in Iceland, New Zealand, Japan, and other volcanically active regions remained warm refugia surrounded by freezing landscapes. Life continued in these oases, completely unaffected by the darkness and cold that devastated everything else. Human survivors clustered around similar strategies: isolation, stored resources, and alternative energy sources. The International Space Station orbited 350 kilometers above the catastrophe. Its crew of 6, let's imagine they were aboard when the impact occurred, watched from orbit as the comet struck. They saw the flash, brilliant even from orbital distance. They saw the fireball expand. They saw the dust plume punch through the atmosphere and spread across the planet below them. They had a perspective no one on the surface could have. They could see the entire catastrophe unfolding in real time. But perspective didn't solve their immediate problem. They had perhaps 6 months of consumables. Food, water, oxygen, all carefully rationed, all finite. Resupply launches from Earth stopped immediately. Ground control, if it still existed, had far more immediate concerns than launching supplies to space. The crew's survival depended on whether anyone down there could organize a rescue mission before supplies ran out, a desperate race against logistics in a collapsing world. Nuclear submarines at sea, when the impact occurred, found themselves in an unexpected position. These vessels are designed for extended patrols with months of endurance. The nuclear reactors can run for years without refueling. They can produce oxygen from seawater through electrolysis. They're essentially self-sufficient, except for food. Imagine the USS Ohio on patrol in the Pacific when the impact occurs. They detect the seismic event. It's impossible to miss on their sensitive instruments. They surface 3 days later to find radio communications disrupted. No response from Naval Command, and emergency broadcasts painting a picture of global catastrophe. The captain faces a terrible decision: dive again and await orders that may never come, or surface permanently and potentially face a dead world. The reactor can run for decades. Their food will last 4 months. Then what? Research stations in Antarctica became unintended arcs. These facilities were already designed for survival in extreme isolation during the Antarctic winter. Months of darkness, temperatures dropping to -80, no possibility of resupply or evacuation. McMurdo Station, the largest Antarctic research facility, was designed to sustain 200 people through winter. When the impact occurred, it held 120 scientists and support staff. They had 6 months of food stores, calculated to last through the normal Antarctic winter. They had fuel reserves for heating. They had greenhouse facilities for growing limited fresh vegetables under artificial light. More importantly, they had institutional knowledge, the accumulated experience of decades of Antarctic operations about surviving in darkness and cold while maintaining morale and preventing the psychological deterioration that comes from isolation. When the rest of the world descended into impact winter, McMurdo was already practiced in the skills that mattered. They knew how to ration. They knew how to maintain life support in extreme conditions. They knew how to keep people psychologically healthy during months of darkness. Their Antarctic winter preparations became survival preparations for a much longer night. The Svalbard Global Seed Vault, built into a mountain on a Norwegian island 800 miles from the North Pole, held over 1 million seed samples from nearly every country on Earth. The facility was specifically designed to preserve agricultural diversity against any catastrophe: war, climate change, natural disaster, or yes, even asteroid impact. The vault required no power. Permafrost provided natural refrigeration, keeping seeds at -18 degrees Celsius. The impact's temperature drop, if anything, helped preserve the seeds. But seeds meant nothing without soil, sunlight, and time to grow. The vault was insurance, a promise to the future that even if surface agriculture failed completely, the genetic diversity of crops would survive to be replanted when conditions improved. Deep underground bunkers built during the Cold War sheltered small populations. These facilities were designed to protect government continuity during nuclear war, to ensure that leadership could survive, communicate, and command forces during the worst-case scenario of global nuclear exchange. Switzerland built a network of fallout shelters capable of housing the entire population during nuclear war. Norway maintained government continuity facilities. The United States had multiple sites. NORAD's Cheyenne Mountain Complex in Colorado, built inside granite, designed to survive direct nuclear strike. Russia had Mount Yamantau and other underground cities. China had vast tunnel networks beneath Beijing. These sites had filtered air systems to remove fallout, stored water, backup power, communication equipment. They were designed for weeks or months of occupation, long enough to wait out the immediate effects of nuclear war. They weren't designed for years, but they were better than nothing. The people who reached these shelters in time had a chance. Those outside, when the impact occurred, generally didn't. Private bunkers varied wildly in sophistication. Some were simple basements stocked with canned food, enough for a few months at best. Others were engineering marvels built by wealthy individuals and corporations, underground complexes with hydroponic gardens for growing food, water recycling systems, air filtration that could operate for years, backup generators, fuel reserves, the most sophisticated, built by tech billionaires in New Zealand and other remote locations, could theoretically sustain small populations indefinitely. But theory and practice differ dramatically. Sustainability depends on more than technology. It requires community cooperation, diverse expertise, psychological resilience, and, frankly, luck. A system failure, a fire, a disease outbreak, or simple human conflict could doom even the best-equipped bunker. Military installations with hardened infrastructure became focal points for survivors. NORAD's Cheyenne Mountain Complex could shelter hundreds. It had independent power from underground hydroelectric, water from underground springs, air filtration designed to handle chemical and biological attacks. Similar facilities existed worldwide, and each became a refuge for those who could reach them. But every bunker, every shelter, every ark faced the same ultimate problem: finite resources in a world producing no new food. You can store food for months or even years. You can recycle water and air indefinitely. But eventually, you must return to the surface and find a way to grow food. Or you die underground with full bellies in a sealed tomb of your own making. The question wasn't just physical survival. Could you stay alive for the next year? The question was genetic survival. Could you preserve enough population diversity to rebuild? Human populations below approximately 500 individuals begin losing genetic diversity through inbreeding. Below 150, the minimum viable population for most species, extinction becomes likely over multiple generations, even if immediate survival is assured. The scattered survivors in bunkers, submarines, research stations, and isolated communities face not just surviving impact winter, but maintaining viable breeding populations. And this required more than food and shelter. It required hope, cooperation, and a willingness to look beyond immediate survival toward a future that might take generations to achieve. But life, as we've seen, is remarkably resilient. From bacteria 3 kilometers underground to tardigrades in cryptobiosis to humans in bunkers, life persists. It finds ways to survive even the worst catastrophes. Evolution has been running this experiment for 3.5 billion years, and life has survived every previous mass extinction, every climate catastrophe, every impact event. This one would be no different. Life would persist, scattered and diminished, but alive. And from those survivors eventually would come recovery. 2 years after impact, the dust has settled. Not metaphorically, literally. The stratospheric dust veil that peaked at blocking 70% of sunlight 6 months after impact has thinned to blocking 30%. The finest particles remain suspended, but most of the dust has fallen out of the atmosphere, coating the planet in a thin layer of pulverized rock. This layer will form a distinctive geological marker in the sediment record. Future geologists, if there are any, will identify this exact year in rock layers worldwide, just as we can identify the KT boundary from the asteroid that killed the dinosaurs. They'll find a thin band of unusual minerals, shocked quartz, and chemical signatures that don't belong, sandwiched between layers of normal sediment. The story of this catastrophe will be written in stone. Sunlight reaches the surface at 70% of normal intensity now. It's still dim. Daylight has a perpetually overcast quality, but it's enough. This is the crucial threshold. Photosynthesis becomes possible again. The process begins slowly in scattered locations favorable by chance or geography, but it begins. In shallow ponds where ice has melted, algae blooms form green patches on the water surface. These are simple organisms, single-celled or colonial, but they're doing something that hasn't happened in sufficient quantities for nearly 2 years. They're converting sunlight into chemical energy. They're creating food from nothing but light water and carbon dioxide. In tropical regions where temperatures never dropped below freezing, where some plants survived in a dormant state, those survivors begin producing new leaves. The growth is tentative, constrained by cold and limited light, but it's growth. Primary productivity, the foundation of all food chains, resumes. The long rebuilding of Earth's biosphere has begun. The temperature stabilizes at 4 degrees below pre-impact levels. It's cold, colder than any human alive has experienced as normal, but it's no longer catastrophically cold. The planet has found a new equilibrium point. The Arctic Ocean remains frozen year-round now. The frozen state has become stable, reflecting more sunlight back to space, which reinforces its own cold in a feedback loop. But mid-latitudes are warming slowly. Spring comes late by the old calendar. May feels like March, June like April. Summer barely arrives. July is mild. August is cool. Fall comes early. September already feels like November. But seasons resume their cycle. The planet breathes again, with an annual rhythm, even if that rhythm is shifted and muted. Pioneer species begin colonization, and here's where we see evolution's strategy for recovery. Ecosystems don't rebuild with the same species that died. They rebuild with species specifically adapted to colonize disturbed environments, fast-growing, generalist, hardy, opportunistic, capable of thriving in poor conditions that would kill more specialized species. Mosses and lichens appear first on bare rock surfaces. These organisms have been doing this for 400 million years, since plants first colonized land. They're the original pioneers. Their strategy is simple but effective. Produce millions of tiny spores, let wind carry them everywhere, and germinate wherever they land. Most die, but some find suitable conditions and establish. Once established, mosses and lichens begin the slow work of making soil. Their acid secretions dissolve rock, breaking down minerals. When they die, their organic matter mixes with rock particles, creating the first primitive soil. Freeze-thaw cycles crack the rock further. Gradually, millimeter by millimeter, soil forms where none existed. Ferns follow close behind mosses. Ferns reproduce by spores like mosses, but they're larger and more complex. They can grow quickly. Some species add visible biomass within weeks. They tolerate poor soil because they evolved to colonize disturbed areas like riverbanks and landslides. The post-impact landscape, covered in dust and ash with minimal organic matter, is ideal for ferns. Within 5 years, fern prairies cover areas that were once forests. Grasses expand from refugia wherever they survived. Grass seeds are remarkable survival capsules. Small, tough, capable of remaining dormant for years or decades. When conditions allow, they germinate. Grasses have a survival advantage built into their biology. They grow from the base rather than the tip, so damage to the top doesn't kill the plant. They can be frozen, chewed by animals, or burned, and they'll regrow from the base. They spread rapidly through runners and rhizomes, underground stems that send up new shoots. A single surviving grass plant can colonize hundreds of square meters within a season. Within 5 years, grasslands are recovering in mid-latitude regions. replacing forests that died and won't return for centuries. Insect populations rebound explosively. And this is where short generation times become crucial. Insects reproduce quickly. Some species complete their entire life cycle, from egg to adult, in weeks. A single surviving pregnant female can produce thousands of descendants in one season, and those descendants produce thousands more. Flies appear first, feeding on the abundant dead organic matter from the die-off. There's no shortage of food for decomposers. Billions of animal corpses, dead plant material, accumulated waste. Fly populations explode. Beetles follow. They're adapted to eating almost anything, and they're extraordinarily diverse. There's a beetle species for almost every possible niche. Bees and butterflies struggle initially because they depend on flowering plants, and flowering plants are still rare. But as pioneer plants begin blooming, simple flowers adapted for wind or generalist pollination, pollinator populations begin recovering. The insect biomass, which crashed by 99% during impact winter, reaches 10% of pre-impact levels within a decade. It's a tiny fraction of what existed before, but it's enough to support the next trophic level. Bird populations face a slower recovery because they need more complex resources than insects. Birds need specific food types, seeds, insects, fish, and they need nesting sites, and many species need specific migration routes with stopover points for feeding. The generalists recover first. Crows, ravens, gulls, species that eat anything and nest anywhere, find the post-impact world challenging but survivable. They're intelligent, adaptable, and opportunistic. They eat carrion when available, insects when they emerge, seeds when plants produce them. They nest in whatever structures survived. Dead trees, rock crevices, ruins of buildings. Specialized birds struggle much more. Warblers that depend on specific insects feeding on specific trees find neither. Shorebirds that migrate thousands of kilometers between breeding and wintering grounds find their traditional stopover wetlands destroyed or changed beyond recognition. Many migratory species simply disappear, their complex life strategies incompatible with a disrupted world. 10 years after impact, ecosystems are assembling into configurations that have no historical precedent. The plants and animals that survived aren't the same mix that existed before. The result is novel ecosystems, new combinations of species creating new relationships that evolution hasn't tested before. In North America, grasslands expand across areas that were deciduous forest for thousands of years. Fast-growing birch and aspen replace slow-growing oak and maple where forest does return. The majestic forests of old-growth trees won't exist for centuries. Those trees take 100 years just to reach maturity. Soil rebuilding proceeds at geological pace, slowly but inexorably. Before the impact, soil contained organic matter accumulated over thousands of years. Each autumn, leaves fell and decomposed. Each year, plants died and their material mixed into the soil. Fungi and bacteria broke down this material, creating rich humus. Earthworms and other soil fauna mixed it, aerated it, and processed it. The surface soil froze during impact winter, and much of its organic matter broke down. New soil must form from scratch through the slow cycle of growth, death, and decomposition. The first-generation soil is thin and poor, little organic matter, few nutrients, low water retention. Plants growing in it are scraggly and small, but each generation adds more. Each year, the soil deepens by millimeters. Over centuries, rich soil develops again. Ocean recovery follows different timelines, and this reveals how different ecosystems operate on different scales. Coastal waters, stirred by waves and currents, receiving nutrients washed from land, recover faster than deep ocean basins. Phytoplankton, with generation times measured in days, rebound within years once light returns to normal levels. Zooplankton follow closely. Their generation times are weeks to months. Small fish follow zooplankton, generation times of 1 to 2 years. Larger fish follow small fish, generation times of several years. But the recovery isn't smooth. It's punctuated by population booms and crashes as species overshoot their food supply, crash from starvation, then recover again when food supply catches up. The system oscillates before stabilizing. Coral reefs face the longest recovery timeline of any ecosystem. Individual corals grow slowly, millimeters per year for most species. Reef structures that took thousands of years to build were destroyed by the impact tsunami in minutes or killed by temperature changes over weeks. The surviving coral fragments begin growing again, but reef recovery operates on century to millennial timescales. 50 years after impact, forests are returning to some regions. These aren't the forests that existed before. Those required centuries of ecological succession. Pioneer species preparing soil, shade-tolerant species replacing pioneers, climax species eventually dominating. These new forests are young, even-aged stands dominated by fast-growing species. In temperate regions, birch, aspen, and pine create dense thickets. These are all pioneer species, adapted for rapid colonization. They grow quickly but live relatively briefly. In tropical regions, bamboo and fast-growing softwoods colonize cleared areas. These pioneer forests are ecologically simple. Few species, single-age class, minimal structural complexity. But they're the beginning of succession toward complexity that will take centuries. Large mammal populations face severe constraints, and this is where we see how population biology limits recovery. Large mammals reproduce slowly. Years between births, few offspring per lifetime, long generation times. The survivors of the initial die-off were reduced to small populations in scattered refugia. These populations can expand slowly, constrained by food availability and the biological reality that you can't rush mammalian reproduction. Deer, elk and bison in North America, or their equivalents worldwide, expand from their refugia at a pace determined by their reproductive biology. A deer population can roughly double every few years under ideal conditions, but conditions aren't ideal. Food is limited. Predators, though rare, still exist. Disease spreads more easily in small populations. Recovery takes generations, not human generations, but deer generations, and that still means decades to approach even a fraction of pre-impact numbers. Predator populations recover even more slowly. Wolves, bears, big cats. These species have large territories and low reproductive rates. A wolf pack might produce 1 litter per year, with only half the pups surviving to adulthood. Bear reproduction is even slower. Females don't breed until several years old, then produce only a couple of cubs every few years. These species take centuries to recover from population crashes. 100 years after impact, roughly 4 human generations if any humans survived, the planet has visibly healed. Vegetation covers most land surfaces again. Forests exist, though they're young and structurally simple compared to pre-impact forests. Animal populations have recovered to perhaps 20% of pre-impact biomass. Ecosystems function again, with complete food chains from plants through herbivores to predators. But the planet is fundamentally different. The species composition is permanently altered. Species that went extinct remain extinct. Evolution hasn't recreated them, and won't. The geographic distribution of surviving species has changed. In North America, species that survived in southern refugia have expanded northward into territories where they never existed before. The resulting ecosystems are novel combinations. Climate has stabilized at the new equilibrium. Average global temperature remains 2 degrees below pre-impact levels. This might not sound dramatic, but it's equivalent to the temperature difference between our current climate and the Little Ice Age of the 16th to 19th centuries. Enough to significantly alter where crops grow, where forests thrive, where deserts expand. The Arctic ice sheet, now permanent year-round, reflects more sunlight back to space. This creates a feedback loop. More ice means more reflection, which means less warming, which means more ice persists. The system has locked into a colder state, and it would take significant external forcing, perhaps thousands of years of gradual warming, to melt that ice again. Ocean circulation patterns have adjusted to the new temperature distribution. The thermohaline circulation, the global conveyor belt of ocean currents driven by temperature and salinity differences, operates differently now. The patterns of upwelling that bring nutrients to the surface have shifted. Fish populations concentrate in different areas than before. 500 years after impact, only an expert observer would notice the difference from pre-impact Earth. Forests have matured. The pioneer species that first colonized are dying off, being replaced by longer-lived species, better adapted to compete in established ecosystems. Old-growth characteristics are developing, dead trees creating snags for cavity-nesting birds, fallen logs decomposing and creating nurse logs for new trees, structural complexity supporting more diverse animal communities. Large mammals roam in numbers approaching pre-impact populations. Apex predators occupy their niches again. Wolves hunt deer and elk in numbers large enough to influence vegetation through their predation pressure. Bears fish salmon runs in rivers where salmon have returned. The ecosystems have achieved something resembling steady state, with energy flowing from sun to plants, to herbivores, to carnivores, to decomposers in stable cycles, but subtle differences remain for those who know what to look for. The species composition is different. Geographic ranges have shifted. In North America, prairies extend farther east than they did before, occupying territory that was once deciduous forest. In the Amazon, certain tree species that dominated pre-impact forests are absent, replaced by different species that happen to survive or to disperse successfully into the recovering forest. 1,000 years after impact, human visitors from another planet, if such visitors existed, wouldn't notice anything unusual about Earth at first glance. The forests are lush and green. The grasslands wave in the wind. The oceans teem with life. Animal populations appear healthy and diverse. By most measures, the planet has recovered. The impact is visible only in the rock record. A geologist collecting core samples would find that distinctive layer. Shocked quartz, iridium anomaly, spherules of melted rock, all the signatures of cosmic impact. Below that layer, fossils of species that went extinct. Above it, fossils of the species that survived and their descendants. The story is written in stone for anyone who knows how to read it. But zoom out to evolutionary timescales, and the impact's influence persists in ways that matter profoundly to the trajectory of life. The survivors became the ancestors of everything that came after. Evolution doesn't happen in a vacuum. It operates on the variation that exists in populations. The impact acted as a massive filter, allowing only certain lineages to pass through. Empty niches create evolutionary opportunities. On islands, where large predators went extinct, small mammals evolved to larger sizes over thousands of generations, filling the empty predator niche. This is called island gigantism, and we've seen it happen naturally on islands isolated from mainland predators. The post-impact world is full of such opportunities. In forests lacking certain tree species, other trees evolve to exploit the resources those species once used. They evolve different growth strategies, different leaf shapes, different tolerances for shade or drought or cold. Natural selection acts on random mutations, and over thousands of generations, species diverge into forms adapted to their new environments. 10,000 years after impact, deep into geological time from a human perspective, but recent history from Earth's perspective, the biosphere has fully recovered its biomass and complexity. The total mass of living things on Earth approaches pre-impact levels. Ecosystems are as complex as they were before, with intricate food webs, specialized niches, and sophisticated relationships between species. New species have evolved to fill niches left empty by extinction. These aren't the same species that went extinct. Evolution doesn't recreate what was lost. They're new forms, adapted to post-impact conditions. The planet is colder than it was, and these new species are adapted to that cold. Seasonal patterns have shifted, and these species are adapted to the new patterns. Ocean chemistry changed slightly due to the massive input of dust and the disruption of normal cycles. New marine species evolve adapted to these changes. Coral species that survive the impact become the dominant reef builders, and the reefs they build have different structure than pre-impact reefs. Fish species adapt to new water temperatures and new food webs, and somewhere in this recovered world, if any survived, might be the descendants of humanity. Changed, adapted, evolved, but carrying forward a lineage that survived Earth's greatest test in millions of years. They would be adapted to the colder world, to the shifted seasons, to the resources available in their refugia. They might not recognize their pre-impact ancestors, and those ancestors might not recognize them. This is the pattern of recovery from mass extinctions. Earth has experienced at least 5 major mass extinctions in its history, events where more than 75% of species went extinct. Each time, life recovered. Each time, the recovery took millions of years to restore biodiversity to pre-extinction levels. Each time, the world that emerged was fundamentally different from the world that existed before. The impact we've explored would rank among the moderate to severe mass extinctions, not the worst Earth has ever experienced, but certainly among the top 10 worst events in the history of multicellular life. And like every previous mass extinction, it would eventually be followed by recovery, diversification, and the evolution of new forms adapted to new conditions. The comet's 4-billion-year journey ended in 1 second of violence. The immediate effects lasted hours. The global catastrophe unfolded over months and years. But the recovery, the healing of the planet, the restoration of its biosphere, that operates on timescales measured in centuries, millennia, and ultimately millions of years. Earth is resilient. Life is resilient. Given enough time, given surviving populations with genetic diversity, given the relentless operation of evolution through natural selection, life rebounds from even the worst catastrophes. The planet that emerges is different, but it's alive, complex, and beautiful in its own way. This is perhaps the most important lesson. The impact would be devastating, but it wouldn't be the end. Not the end of Earth, not the end of life, and potentially not the end of humanity. If we prepare, if we survive, if we adapt, the planet would heal, life would continue, and eventually, the catastrophe would be nothing but a thin layer in the rock record and a story told by those who survived, if there's anyone left to tell it. The scenario we've explored over these chapters is hypothetical. 3I/Atlas didn't hit Earth. It passed safely through our solar system and is now heading back into interstellar space, never to return. But the physics underlying everything we've discussed is absolutely real. Cosmic impacts aren't science fiction. They're science fact, an ongoing hazard that Earth faces every single day. The question isn't whether impacts happen. We know they do. The question is when the next significant one will occur and what we can do about it. Earth's surface tells the impact story in craters scattered across every continent. Meteor Crater in Arizona is one of the most accessible and well-preserved examples. 1.2 kilometers across, 170 meters deep. It formed 50,000 years ago when an iron meteorite, 50 meters wide, struck the desert at 12 kilometers per second. The explosion released energy equivalent to 10 megatons of TNT, roughly 700 Hiroshima bombs. Everything within 4 kilometers was vaporized or obliterated instantly. Trees, if any existed in that desert environment, were flattened for 8 kilometers in all directions. The shockwave could be felt for hundreds of kilometers. The indigenous people who lived in the region told stories passed down through generations about fire falling from the sky. These stories might preserve the memory of that impact across 500 generations of oral tradition. But Meteor Crater is tiny compared to what's possible. The Chicxulub crater, buried under Mexico's Yucatan Peninsula and the Gulf of Mexico, tells a far more dramatic story. Measuring 180 kilometers in diameter, it marks the impact. Site of an asteroid 10 to 15 kilometers wide that struck 65 million years ago. The energy released exceeded 100 million megatons, 5 billion times more powerful than the atomic bomb dropped on Hiroshima, a number so large it becomes almost meaningless. The impact ended the Cretaceous period and the reign of dinosaurs. 3/4 of all species on Earth went extinct. The geological boundary marking this event, called the KT boundary or Cretaceous-Paleogene boundary, appears in rock formations worldwide. You can visit outcrops where this boundary is visible. It's a thin layer of clay, usually just a few centimeters thick, sandwiched between limestone, containing fossil shells and other marine organisms below, and very different rock above with far fewer fossils. That clay layer is enriched in iridium, an element rare in Earth's crust but common in asteroids. It's a signature written in chemistry. Something from space struck Earth and spread its material globally. The Tunguska event in 1908 provides a more recent example and demonstrates that impacts happen in modern times, not just geological history. On June 30th, over remote Siberian forest, an object, probably a small asteroid or comet fragment about 40 meters across, exploded in the atmosphere with force equivalent to 10 to 15 megatons. The airburst flattened 80 million trees across 2,150 square kilometers. No crater formed because the object disintegrated entirely before reaching the ground, but seismic stations worldwide recorded the shockwave. The explosion occurred at an altitude of about 5 to 10 kilometers, and the downward directed energy created devastation comparable to a nuclear weapon. Here's what makes Tunguska particularly sobering. If it had occurred over Moscow, St. Petersburg, London, or any major city instead of uninhabited Siberian forest, casualties would have numbered in the hundreds of thousands. The object was detected by no one. There was no warning. One moment the day was normal, the next moment the sky exploded. Even more recently, the Chelyabinsk meteor in 2013 reminded the modern world that space is full of debris, and we're not as safe as we'd like to think. On February 15th, a meteor about 20 meters across entered the atmosphere over Russia at 19 kilometers per second. It exploded at 30 kilometers altitude with force equivalent to 500 kilotons, roughly 30 times the Hiroshima bomb. The airburst shattered windows across 6 cities, injuring over 1,500 people, mostly from flying glass. The shockwave was powerful enough to damage buildings and knock people off their feet. Dashboard cameras across the region, common. In Russia, for insurance purposes, captured unprecedented footage of the fireball's descent, giving us detailed documentation of what a medium-sized impact event looks like. Here's the critical point. The Chelyabinsk meteor wasn't detected before entry. It approached from the direction of the sun, our blind spot, where telescopes can't look without being blinded by solar glare. We had zero warning. The first indication that something was happening was when it entered the atmosphere and began to glow. Cataloging the threat requires understanding what's actually out there. Near-Earth objects, asteroids and comets with orbits that bring them close to Earth, number in the hundreds of thousands. We've discovered roughly 30,000 so far, but that's a small fraction of what exists. NASA's Near-Earth Object Program, established in 1998, coordinates the effort to detect and track these objects. The program's congressional mandate was specific. Find 90% of NEOs larger than 140 meters in diameter by 2020. Objects this size can cause regional destruction, devastate an area the size of a small country, generate massive tsunamis if they hit ocean, fundamentally disrupt global infrastructure, even if the impact is in a remote area. Current surveys have identified approximately 90% of NEOs larger than 1 kilometer, the ones capable of causing global catastrophe like the scenario we've explored in previous chapters. About 1,000 such objects exist in near-Earth space, and the good news is that none currently pose impact threats within the next century. Their orbits are well characterized, and we can predict their positions decades in advance with high confidence. But the catalog remains dangerously incomplete for smaller objects. We've identified only about 30% of objects in the 140-meter range. That means roughly 20,000 objects large enough to destroy a major city or generate a devastating tsunami remain undiscovered. They're out there, and we don't know where they are or when one might be on a collision course with Earth. Detection depends on telescopes scanning the night sky, looking for points of light that move against the background of distant stars. The Pan-STARRS telescopes in Hawaii, the Catalina Sky Survey in Arizona, NASA's NEOWISE space telescope, and other survey programs collectively discover dozens of new NEOs every month. But the detection process has fundamental limitations. Objects are easiest to detect when they're close, which gives minimal warning time, and when they're illuminated by the sun from Earth's perspective. Objects that are far away are too faint to see. Objects near the sun in the sky are invisible because they're lost in solar glare. We can only search the night sky away from the sun, which means we have a blind spot. Once an object is detected, tracking determines whether it poses a threat. Astronomers measure the object's position precisely over multiple nights, sometimes months if the object is faint or distant, and use those measurements to calculate its orbit. Orbital mechanics, the same mathematics Newton developed 300 years ago, allows predicting future positions with remarkable accuracy. Most asteroids pose no threat. Their orbits miss Earth by comfortable margins measured in millions of kilometers. But some orbits cross Earth's path. These objects might strike Earth or might miss by millions of kilometers, depending on exactly where Earth and asteroid are in their respective orbits when their paths intersect. Calculating impact probability requires knowing the orbit precisely, which requires extensive observations. Asteroid Apophis provides an instructive example of this process. Discovered in 2004, early calculations based on limited observations suggested a 2.7% chance of impact in 2029. That might sound like low probability, but for an asteroid 370 meters wide, large enough to devastate an entire region, a nearly 3% chance of impact was absolutely terrifying. Additional observations over subsequent years refined the orbit. By 2013, astronomers could confidently rule out impact in 2029. Apophis will pass close, within 30,000 kilometers, closer than geosynchronous satellites orbit, but it will miss. The event demonstrates both the detection system working as intended and the critical need for precise orbital tracking. Some asteroids remain concerning. Bennu, a 500-meter asteroid, has approximately a 1 in 2,700 chance of impacting Earth sometime in the late 2100s. Those odds sound low, and they are. It almost certainly won't hit us. But for an object that could devastate an area the size of Texas and trigger global climate effects, even small probabilities demand attention. NASA's OSIRIS-REx mission visited Bennu, mapped it in extraordinary detail, and collected samples from its surface that were returned to Earth. The mission had multiple objectives, but one was improving our understanding of Bennu's orbit and physical properties to better assess impact risk and inform potential deflection strategies. Deflection, changing an asteroid's orbit so it misses Earth instead of hitting, is feasible with current technology, but only if we have sufficient warning time. The Double Asteroid Redirection Test, DART, launched in 2021 and successfully struck the asteroid Dimorphos in September 2022. Dimorphos orbits a larger asteroid called Didymos, making it a binary asteroid system. DART was a kinetic impactor, essentially a spacecraft designed to crash into the asteroid at high speed. The collision changed Dimorphos's orbital period around Didymos by 33 minutes, proof of concept that we can alter asteroid trajectories. This might not sound impressive, 33 minutes out of an 11-hour orbital period, but here's why. It matters. A small velocity change applied years before a potential impact translates to missing Earth by thousands or millions of kilometers. The earlier you deflect an asteroid, the less deflection you need. Applied months before impact, even large velocity changes might not be sufficient to turn a hit into a miss. The strategy must be preventive, not reactive. We need decades of warning, which requires detecting threats as early as possible. This is why survey programs focus on finding hazardous asteroids now, decades before any potential impacts, so we have time to respond. Alternative deflection methods exist for different scenarios. Gravity tractors, spacecraft, that hover near an asteroid and use their own gravitational attraction to gradually alter its orbit, work. For small course corrections given long warning times and relatively small asteroids, the deflection is tiny but continuous over years. Nuclear devices detonated near an asteroid's surface to vaporize material that jets away and creates thrust like a rocket, provide maximum deflection force but carry obvious political complications. There's an international treaty banning nuclear weapons in space, though it includes exceptions for peaceful purposes like planetary defense. John Beam shepherds spacecraft that fire ion engines at the asteroid's surface to ablate material and create thrust, offer precise control for slow, continuous deflection. Each method has advantages and disadvantages depending on asteroid size, composition, warning time, and required velocity change. Comet threats differ fundamentally from asteroid threats. Comets originate in the outer solar system, either the Kuiper belt beyond Neptune or the Oort cloud surrounding the solar system at vast distances. They follow highly elongated orbits that occasionally bring them through the inner solar system, where Earth orbits. Long-period comets, those with orbital periods exceeding 200 years, pose the greatest detection challenge. They spend most of their time far from the Sun, where they're too faint to see. A comet might be detected only months before perihelion, closest approach to the Sun, when it becomes bright enough for telescopes to spot. If that comet's orbit happens to cross Earth's path, warning time could be extremely short. Comets also move faster than asteroids when they're near Earth because they're falling inward from the outer solar system. Higher velocity means more kinetic energy, which means more destructive potential. Deflecting a comet requires more energy than deflecting an equivalent-sized asteroid, and we might have less time to do it. Interstellar objects add yet another layer of complexity. Oumuamua in 2017 and Comet 2I/Borisov in 2019 demonstrated that objects from other star systems occasionally pass through our solar system. These objects aren't gravitationally bound to the Sun. They're just passing through on hyperbolic trajectories determined by their motion through the galaxy. They move fast, often faster than solar system objects because they retain the velocities they had in interstellar space, plus whatever velocity they gain falling. Toward the Sun, they approach from unpredictable directions determined by galactic dynamics rather than the plane of the solar system, where most objects orbit. Detecting an interstellar object on collision course with Earth would provide minimal warning, perhaps months at best, possibly less. The statistical risk of impacts can be calculated based on crater counts, observed near-Earth object populations, and orbital dynamics. Objects large enough to cause global catastrophe, 1 kilometer or larger, strike Earth approximately once every 500,000 to 1 million years on average. Regional scale impactors, 100 to 300 meters, hit roughly once every 10,000 years. City destroyers like the Chelyabinsk object strike every few decades. These are statistical averages. The actual timing is random. Earth might go 2 million years without a major impact, then experience two in quick succession. There's no pattern, no schedule, just probability playing out over time. The difference between astronomical hazard and existential threat depends entirely on preparation. With no detection or deflection capability, humanity is vulnerable to random chance, a cosmic roll of the dice where the stakes are civilization itself. With robust detection and proven deflection technology, most threats can be neutralized given sufficient warning. Our current state is transitional. We have partial detection coverage, good for large objects, poor for medium-sized objects, essentially blind to small objects and anything approaching from the sun's direction. We have demonstrated but limited deflection capability. DART proved the concept, but we haven't built operational deflection systems ready to launch on short notice. Investment in planetary defense has increased following proof of concept missions. ANEO Surveyor, a planned infrared space telescope, will detect asteroids currently missed by ground-based surveys, particularly those in orbits that keep them near the sun in the sky where ground telescopes can't look. Infrared detection works because asteroids emit heat radiation that's visible even when they're not illuminated by the sun from our perspective. International cooperation is developing through the United Nations Committee on the Peaceful Uses of Outer Space, which coordinates impact threat information sharing and response planning. Multiple nations have expressed commitment to contributing to deflection missions if needed. There's growing recognition that planetary defense is a global challenge requiring global cooperation. The scenario of 3I/Atlas colliding with Earth serves a crucial purpose, even though it's hypothetical. It forces contemplation of planetary-scale catastrophe and the measures needed to prevent it. The physics of impacts, the cascading environmental effects, the survival challenges, the recovery timelines, none of this is speculation. It's based on evidence from past impacts, laboratory experiments, computer modeling, and our growing understanding of how planets and ecosystems respond to catastrophic disturbances. Understanding these processes motivates investment in detection and deflection before they're desperately needed. It's far better to build planetary defense systems during peacetime, when we have the luxury of time and resources, than to scramble in crisis when a threat is detected with insufficient time to respond. Earth will face another significant impact eventually. That's not pessimism or fear-mongering. It's orbital mechanics and probability. Millions of asteroids cross Earth's orbit. Billions of comets orbit in distant reservoirs. Some will eventually be perturbed onto collision courses with our planet. The only questions are when and whether we'll be ready. The story of 3I/Atlas is both cautionary tale and call to action. It reminds us that our planet orbits through a shooting gallery, that space is not empty but filled with debris from the solar system's formation, and that vigilance is the price of survival. But it also reminds us that we're not helpless. Unlike the dinosaurs, we have the technology to see threats coming and potentially to prevent them. We stand at a unique moment in Earth's history. For 4 billion years, life on this planet was vulnerable to cosmic impacts with no way to prevent them. Impacts occurred, and life either survived or didn't, based purely on chance. Now, for the first time, a species has developed the capability to detect threats and potentially defend against them. Whether we choose to invest in that capability, whether we build and maintain the systems needed for planetary defense, whether we treat this as the existential priority it deserves, these are decisions we make collectively as a civilization. The universe doesn't care whether we survive. The asteroids and comets continue their orbits regardless of what we do. The only question is whether we'll prepare, whether we'll detect the next threat in time, and whether we'll have the capability to respond. The 4-billion-year journey of an interstellar comet ending in catastrophic collision with Earth is hypothetical. But somewhere right now, there might be an asteroid or comet on an orbit that will eventually bring it to Earth. We might have detected it already and know it's not a threat. Or we might not have detected it yet. Or it might be approaching from our blind spot, visible only when it's too late to do anything but watch. This is why we search the skies. This is why we build better telescopes. This is why we test deflection technologies. This is why planetary defense matters. Because the next impact isn't a question of if, it's a question of when. And whether that impact is a catastrophe or a near miss that becomes a footnote in history depends on what we do now, today, before the threat appears. The choice is ours. The technology exists. The physics is understood. What's required now is commitment, the collective decision that protecting Earth from cosmic impacts is worth the investment, worth the international cooperation, worth building and maintaining systems we hope never to use, because vigilance is the price of survival. And in the cosmic shooting gallery we call the solar system, the only way to survive is to watch, to prepare, and to be ready to act when, not if, but when, the next threat appears.